I want to talk about time resolved measurements, and I'm going to start the talk by giving a little bit of an overview of some of the different techniques that are being used to do ultra-fast studies of single objects using microscopy. I won't spend too much time on this, and this is not meant to be a complete description of all the techniques, just to highlight a couple of points. And then after doing that, I'll talk very briefly about doing imaging of charge carriers and excitons and even plasmons moving around nanostructures, and then talk about some transient absorption experiments and a little bit of detail that we've been doing on metal nanostructures and how they interact with their environment. Okay, so there are a variety of different ways that you can do an ultrafast measurement on a single nanostructure. And I've sort of arranged them in orders of highest spatial resolution going down to lowest spatial resolution, and also somewhat in orders of complexity. So all of these time resolved measurements are done using pump probe techniques where you have, well, two laser pulses, one that excites the sample and another one that you use as a probe. Probably the technique that has the most promise for really high spatial resolution is the one that's been advocated by the Zewail group, and well, the people who are now working on this, many of them are from the Zewail group, and that's to do ultra-fast electron microscopy. So the idea here is you have a laser pulse that excites the sample. In these experiments by Flanagan and University of Minnesota, it's a green pump pulse. And then you use a second pulse to generate a bunch of electrons by hitting a material and having electron emission. You collimate those electrons and then pass them through the sample, and you use the electrons to image the sample. Right, this is a very complex experiment. The example at the bottom here is looking at some strain waves moving through a sample after exciting a material, and so you can sort of see these waves propagating through the material. So you can get very high spatial resolution with this technique. The time resolution is not that great because it comes from the electrons, and it's very hard to keep the electrons together in a little bunch as they pass through the sample. They repel each other, and that spreads out the electron pulse. The sensitivity is also really quite low. At least it hasn't very high sensitivity. Studies of small particles has not been demonstrated so far. You can also use electrons to image materials by doing a photo emission electron microscopy experiment. So in these experiments, you use a pump laser pulse to excite a material, you excite electrons, and then you ionize the electrons with a second pulse. So if you image the electrons, you can get high resolution. And at the bottom here are some examples of looking at plasmon modes propagating in what I think are silver nanoparticles. So in these experiments, the plasmons were excited by laser pulse. They are created at the edges of the nanostructure and they move inwards. And then you use the second laser pulse to ionize the electrons and create an image, a sort of instantaneous image of the electrons at the surface of the structure. What's interesting about these images is that when you look at them, you can see waves that represent the wavelength of the plasmons moving in the structure. And there are two waves in the thin particles that are on the right-hand side of the image. You see you see two waves, a long wavelength period and a shorter wavelength period. In the thicker structure, you only see the long wavelength motions, and those come from plasmons that are propagating on both the top and the bottom surface of the plates. Okay, so you get the one at the top is what's called a leaky mode. It has a longer wavelength, and the one at the bottom is a bound mode. It has a shorter wavelength. And you see the one at the bottom for the thin plate. For the thicker plate, you don't image the field from the bottom of the structure. What's interesting about this measurement, right, is that you don't need to use much optics for the laser pulse. So in principle, you can get very, very high time resolution in this experiment. It's determined by the cross correlation between the pump and the probe beams. You can also get very high spatial resolution by doing near field experiments. they can be done in two ways. You can do a scattering experiment at the bottom where you focus a pump and a probe beam at a sample, and then you scatter light using typically an AFM cantilever, and detect the probe light in the detector. Or you can use a fiber and pass a laser beam down through a small aperture in the end of a fiber to get high spatial resolution. In both these cases, you can get very high time resolution. Clearly, it's rather complicated to do that when you pass your laser beam down through a fiber, but it is possible. So these are ways you can get, well, high spatial resolution and, in both cases, high time resolution. For the scattering technique, the high time resolution, again, is fairly easy to achieve because you just take short laser pulses and you focus them on your sample. You don't need to use objectives, which will broaden things out. Okay, all of those techniques are quite complex, right, to do and difficult. And they're also a bit limited, right? You can't do things in any of those techniques really for things in solutions. When you use electrons, or if you try to do ultrafast X-ray scattering, which has also been done on single particles, you have to do things in vacuum. So they're not very flexible techniques. What we prefer to do is to simply do far-field transient absorption microscopy, which was talked about a little bit in not Ken's talk, but the one before that. And so in these experiments, you take a laser system, typically a high repetition rate laser. You make a pump and a probe beam. You modulate the pump beam at a very high frequency using, we use an acousto-optic modulator, or you could use an electro-optic modulator. Then you focus the two beams at a sample. So if you use a very high numerical aperture objective, you can, of course, get high spatial resolution. And the other thing about this is that when you focus the beam to a small spot at the sample, you get increased sensitivity too. So the diagram on this slide of the focused beam is sort of for a 530, 550 nanometer beam or so, using a 1.3 NA objective. And it's sort of drawn out to show the size of the beam compared to the size of a 20 nanometer gold particle. So under those focusing conditions, right, that gold particle will absorb an amount of light about 1% of the beam, okay? And that calculation is the absorption cross-section of the particle divided by the area of the beam. Okay, so that's not much, right? And when we do a transient absorption experiment, the signal levels are typically about 1,000 times smaller. For metals, the signal levels are about 1,000 times smaller than the absorption of the objects. So in a transient absorption experiment, you would expect a signal level of about change in the intensity of the probe of about 10 to the minus 5. Okay, so very small signals. But if you use a high repetition rate laser that's very stable, then you can get signal to noise levels of about 10 to the minus 7. So for a 20 nanometer gold particle, you should have a signal to noise of roughly a few hundred to 1. And that's what we see in these images over on the left-hand side here. So we get pretty high signal to noise, and we get that because we have a very stable laser system, and we're focusing the beams very tightly. So the absorption cross-section of the particle compared to the area of the beam is as high as it can be. The images on the right, at least the right of my screen, are some semiconductor nanowires in some work we did with Ken. And the point to show these images is that, well, we can image semiconductors as well as metals. I'm mainly going to talk about metals when I go through this talk. But the other thing is that these were experiments done with different probe laser powers. And what we see in this experiment is that as we increase the power of the probe beam, the signal to noise level in the experiments also increases. So that shows that we're shot noise limited, which is good and bad, right? The good thing is that we're shot noise limited. You can't really do better than that in this sort of measurement in terms of sensitivity. The bad thing is that we can't do any better than what we're doing right now. So we're sort of stuck at this level. Practically for us, we can image particles, metal particles down to probably about 5 nanometers, maybe a little bit smaller. If we want to study something about the particle, like look at its dynamics and how it interacts with the environments, we typically look at objects that are about 10 nanometers, 20 nanometers or larger. Okay, so even though we can image very small particles, we can't really learn much about them. Indeed, with these experiments, we've imaged single wall carbon nanotubes, which have a diameter of about 1 nanometer. They're very small, but all we could really do was image them. We couldn't really measure anything about them. Okay, this slide has a sort of a comparison of some of these different techniques. I've included some ultrafast X-ray measurements. Like Ken, you can sort of see lots of red crosses. I have a preference against big instrument sort of projects. So ultrafast electron microscopy, ultrafast X-ray measurements, these are very big machines, very expensive. They typically are not very sensitive. So that's a disadvantage. They're not very flexible because you can only study things in vacuum. And they also often don't have really great time resolution. Experimental techniques where you don't need to use an objective to focus at the sample, like in time-resolved photoelectron measurements or scattering near-field optical measurements. In those experiments, you can get very high time resolution because you don't have to worry about the dispersion. For us, we use refractive objectives, right? So we are limited by the dispersion in the objective. There are ways that you can do far-field transient absorption measurements without passing the pump and probe beam through an objective, and maybe Dario will talk about those a little bit later. So it is possible to get better time resolution than what we have. We have about 300 to femtoseconds to half a picosecond sort of time resolution. Okay, the far-field techniques are sensitive, right? They're not as sensitive as techniques where you try to detect emission from the sample, but they're very flexible and they're relatively cheap, right? You can study things in liquids and all sorts of different types of samples. So the images on the previous slide, where we were looking at the experimental setup, they were done in the way that you'd normally do an image, right? You overlap your pump and probe beam at the sample, and then you scan the sample through the pump and probe beam. Now, clearly, of course, you could use a galvo mirrors to scan the beams over the sample, but in those experiments, the two beams with the pump and the probe were spatially overlapped and also temporarily overlapped to give the biggest signal. Okay, in these techniques, you can do a different sort of imaging measurement that's actually extremely useful. You can do experiments where you hold the pump beam fixed at the sample, and then you scan the probe beam over the sample using, just scanning mirrors, right? You separate the two beams and you scan the probe relative to the sample. In those sort of experiments, you can create excitation in the material, like charge carriers or excitons, and then you can image how those things spread out in time after you've excited them. So the first example up on the left is some experiments done by John Papadopoulos and his co-workers at University of North Carolina, Chapel Hill, where they excite some charge carriers in a single silicon nanowire. Then they scan the probe over the sample and watch how the charge carriers move to fuse away from the excitation spot in time. And then by analyzing the change in the distribution, they can work out a diffusion constant for the charge carriers in the nanowire. On the right is some examples from Libai Huang's group at Purdue University, where they're looking at the motion of singlets and triplets in organic crystals. So by choosing the wavelength of the probe, they can either probe the singlets or the triplets. And so again, you can watch them after you've excited them, you can watch them diffuse around the sample. And this gives you a lot of information about what's happening to the species that you create. We mainly work with metals, and so we look at plasmons. So on the bottom is an experiment with the gold nanoplate. I'll say a lot about nanoplates in a little bit. What we've done here is we've excited the pump laser at the edge of the nanoplate. When you do that, you excite propagating plasmon modes that move along the surfaces of the plates. As I briefly said a little bit earlier, you get two sorts of modes. You get ones that move along the top of the plate at the metal air interface in this experiment, and you also, the plates are supported on glass. You also get modes that move at the bottom of the plate at the metal glass interface. These are these bound and leaking modes, and they have different wave vectors. So in the electron microscopy measurements, you have the spatial resolution to image the wave vector or the wavelength of both of those plasmon modes, so you directly see the wavelengths. In an optical experiment, you don't have the spatial resolution to image a plasmon mode, just because of the difference in momentum between electrons and photons, so you can't see that. We see waves in our experiments that you can see quite clearly in panel A, and what's happening here is that we're looking at the interference between the two modes, the one at the bottom and the one at the top of the plate. So they have different wave vectors. When they overlap, there's an interference effect, and that's what we see in the transient absorption experiment. Right? We can calculate out what that wavelength should be, and we get very good agreement. The image at the bottom, which I don't really like to talk about a lot, what we did in that experiment is that we repeated the experiment but just put water on top of the plate. So that changes the environment and it changes the wave vectors of the plasmon modes, and so you get a different interference pattern. The two modes now have a similar wave vector, so the wavelength of the interference pattern gets a lot longer. Okay, so I'm going to talk for the rest of the talk about not doing imaging experiments, but just overlapping the pump and probe and the microscope, overlapping them spatially, and then looking at how the signal changes as a function of time. And most of what we're going to, well, all I'm going to talk about is metal particles. And one of the reasons for that, of course, is that metal particles absorb light fairly strongly. They're pretty tough, so that you can excite them with your laser beams with fairly high powers without destroying them. And so they're good systems to do these experiments. So the two examples here, the one on the left is experiments that were done in my lab on some chemically synthesized gold nanowires. And in the top, we see some SEM images of these wires. This is a very big wire, so we could actually look at the cross-section of the wire and work out its size. And then on the right-hand side are some experiments done by the Vallée and Delfatti group in Lyon, where they're looking at particles that have been made by nanolithography, and so they're stuck on the surface. In these experiments, if we sort of look at the trace on the left-hand side, as a function of time, what you see is a very fast signal that decays, and that's in panel B. So what we do when you shine light at a metal is you excite the electrons. The electrons will lose their energy. They'll equilibrate with the phonon modes of the particle. That's electron-phonon coupling. That happens in a few picoseconds for these objects. And the result of that process is that you heat up the object. And so that can excite vibrational modes of the object. And these vibrational modes are what cause these little oscillations in the transient absorption traces. So for the wire that so what you normally do, or almost exclusively do, is when you shine an ultrafast pulse at a metal nanoparticle, you excite the breathing modes of the particle. For the wire on the left-hand images, this wire is faceted. It has a pentagonal structure. And so there are two breathing modes, one corresponding to motion at the faces and one corresponding to motion at the apexes of the structure. And that's why we see this interference pattern in the beats as a function of time. The measured frequencies in that experiment, we can calculate what it is through finite element simulations, and we get a very good match because we know the dimensions of the structure. In the experiments by Vallée on the right, you also see breathing modes. This is a larger object, so the periods are a bit slower. They're about, well, actually that's not true. They're both about 10 gigahertz or so for both of those objects. Both of those are quite large. When you have a nanoparticle stuck on the surface, like when you make them by nanolithography, the lifetimes of the breathing modes, which we normally think about through the quality factor, basically the lifetime divided by the period, the the lifetime/quality factors are quite small, and that's because the energy of these acoustic modes is going into the substrate. For the wires here, what we've done is that we've put it on a surface where there are trenches cut in the surface, and then if we look at the part of the wire that is suspended over the trench, we don't have this energy loss into the substrate, and so we get much longer lifetimes, and that's good for a couple of reasons. Okay? The first one being, of course, it makes the measurement a little bit easier. The second thing that we're interested in is when we have these suspended structures, we can actually look at how the lifetime changes when we add, when we change the environment. So this is an example of such an experiment. We have some nanowires, a cartoon now, some nanowires suspended over some trenches. What we've done here is we've measured the vibrational modes and the lifetimes of the nanowire and air, and then we've added water to the sample and we've remeasured, and then the difference between those two experiments tells us about the damping of the acoustic modes due to the liquid. Now, the reason that we spent a lot of time doing this, and the reason that we decided that we did this project, was that these acoustic modes, if you make the wires relatively small, right, they have quite high frequencies. And the frequencies start to approach the relaxation times of the liquids, of the simple liquids that you can get. And so this is a situation where one might start to see viscoelastic effects in the response of the liquid to this vibrating object in the liquid. And I have a mathematician friend in Australia, John Sader, who told me that this was very interesting because people didn't know, mathematicians didn't know much about viscoelastic effects at the nanoscale. And of course, I knew nothing about it, so I believed him. And so he encouraged us to sort of look at this to try and see if we would measure this, could measure this effect, this, basically the effect of the relaxation time of the liquid. So what we did is we measured for these wires that have vibrational modes with frequencies of around about 50 gigahertz. We measured their response in a whole bunch of liquids, and then we compared that to calculations done both by myself and by John. And so that's on the right-hand panel. And so if you look at the quality factors, which again are basically the lifetimes, you see that they matched this line now that we've drawn through the data. So that line is actually a calculation where the liquid is just treated like it was a solid. So that, without thinking about viscosity or viscoelastic effects in the liquid at all, you get a pretty good match to the experiment. The circles on that line are calculations by John, where he's included the viscoelasticity in the liquid and done a finite element calculation. And again, that matches the line. And so the conclusion from this is, after really what for us was quite a lot of work, is that, well, you actually don't see viscoelastic effects in these particular experiments. What happens is that you just have radiation of sound waves from the particle into the liquid. The liquid behaves like it's a solid. Right, viscosity doesn't seem to matter at all for these liquids, and John would call that an inviscid compressible flow. It's just radiation of sound waves. Okay, it's very a little disappointing after all that work that we didn't really measure anything about viscoelasticity. And there are two problems with the experiment. One is that, well, the vibrational modes actually weren't all that high. They're only about 50 gigahertz. Well, that's high, but not high enough apparently. And also, you know, there's a lot of noise in the measurement, so it's hard to do the experiment very accurately. These symbols here are the results of 10, sometimes 50 sort of experiments on individual wires averaged together. Okay, so what we want, if we want to do this, and what we want in general, is to have nanoparticles that have very long lifetimes. So you have much higher quality factors and you can measure things much more accurately. So it turns out if you don't do wires, if you do plates, you can get much, much higher quality factors. And this is what's shown in this slide here. So on the left is some images and a transient absorption trace for a gold nanoplate that's suspended over a trench in a substrate done in my lab. And you can see now that you have the vibrations go on for a very, very long time. Again, it's the breathing mode of the plate, but we get a very high quality factor. And on the right is some experiments done by our collaborators in China, who are again looking at gold nanoplates, but now they're suspended on a wholly carbon TEM grid. So a substrate that's very, very light and doesn't affect the particle very much. Again, you get very high quality factors. For these plates, you can get quality factors that are well over 100. And you can start to see, you can also get very high frequencies if you can find plates that are very thin. So the high quality factors actually allows you to measure these vibrations very accurately, which is good. And so I'll show a couple of things about that. Okay, the first is that if you can measure the vibrations accurately, you can see how they couple to each other. So this is an example of an experiment where we have, well, my collaborators have found two plates that are just on top of each other, just randomly from the sample. So in this experiment, if you do a measurement on one of the plates, you'll see one frequency. If you go to the other plate, you'll see a different frequency. And then if you look in the region in between where the two plates overlap, you again see, now you see two frequencies, but the two frequencies are different from the parts of the sample where you just have a single plate. And so what's happening here is the two vibrations are coupling to each other, and you see a change in the frequency. If you look at enough plates, you can sort of have an estimate of the coupling strength, and the coupling strength for this system is on the order of about 10% of the frequencies. So you get actually very strong vibrational coupling in this system when you look at these overlap plates. Okay, you'll also see here there's a frequency that we've labeled as FREL. That's what we call a relative mode. You also see a frequency from the plates sort of moving relative to each other. That's a much lower frequency. Another thing that you can do when you have these very high quality factors for these particular materials is that you can look at them as being nanoscale mass sensors. So I think probably the best thing to do is just to look at the bottom set of slides, bottom images. This is again a nanoplate that was suspended over a trench. And in this experiment, what we've done is we've dropped some polystyrene beads on top of the plate. I think they're about 100 nanometers diameter. And so when we do experiments on the plate in a region where there are no beads, we see one vibrational frequency. And then when we do an experiment on the plate in a region where there are beads, we see a different vibrational frequency. It's shifted to lower frequency, and that comes about from a mass loading effect. So this is potentially an example of possibly being able to use these materials to do mass sensing experiments, right? Because the difference in the frequency informs you about the mass of the object that's on top of the plate. The traces on the top were just experiments where we looked at the same plates before and after plasma cleaning to remove the organic material from the surface of the plates. And what we see in all of the different plates that we looked at is there's an increase in the frequency because we've now, in this case, we've got rid of mass by the cleaning process. Okay, the last set of experiments that I have, some very recent ones, again done by Kwai at Szechuan University. These are on, again, nanoplates that are very, very thin. So now they have very high vibrational frequencies. And so in these experiments, Kwai has suspended them over a substrate, a TEM grid where there are holes in the substrate. It's a membrane. And so you can do experiments on the plates that are suspended over the hole. So again, you get very high quality factors, so you can measure the frequencies very accurately. And then we've done the experiment that we tried a bit earlier with the nanowires. So we look at the plates in air, we measure the frequency and the vibrational lifetime, then we add a liquid. Here we've added liquid, water, and then different water glycerol mixtures. And then we remeasure the lifetimes to see how they change when we add the liquid. Okay, so what we saw before is that we were not very accurate enough in our experiments, so we couldn't tell the difference between the different models for how the liquid should damp the vibrations. With these nanoplates, because the frequencies are much higher, they get much closer to the relaxation times of the liquid. So now we start to see differences between the different models. So in the bottom panel that's labeled C here, we have the experimental measurements of the quality factors for our plates for different water glycerol mixtures in the red. And then we have calculations of what we'd expect the damping to be for those different mixtures based on 3 models. Right, so the 3 models are what's called the Envisage model, where you just think of the liquid as behaving like a solid. There's no viscosity. You just have sound waves radiating out from the particle that take the energy away. And we can clearly see that a difference between our data and that model, whereas we couldn't see that before. The 2 other lines, the green and the blue line, are calculations for a viscous liquid, where we include the viscosity of the liquid in the calculation, but we don't include its relaxation time. And then the blue is a calculation where we include viscoelastic effects, so we include the relaxation time in the model, and that's just done in this by modifying the viscosity in the way that's shown on the left there. Okay, so at small weight percents of glycerol, so like in solutions that are mostly water, we can tell that our data don't match the Envisage model, but they do, the viscous and viscoelastic models account for the data pretty well. But once you get to very high weight percents of glycerol, it's clear that the viscous model fails quite badly, and that the viscoelastic model is the correct description. The panel on the right shows our measurements. We can use these results to measure the relaxation times in the liquid, and you can sort of see that we're in reasonable agreement with the literature values for the relaxation time. All right, so when we have samples with very high quality factors and high vibrational frequencies, then at last we can start to see these viscoelastic effects, and we can actually use these measurements to estimate the relaxation times in the different liquids. Okay, and so that is the end of my my talk. So transient absorption microscopy, right? It's actually a very flexible technique. You can study lots of different things. It can be very sensitive, and I think the challenges are how to do this now with very high time resolution. Time resolution is not a super big deal for us because we're looking at these vibrations that don't require, sub 100 femtosecond sort of time resolution. But of course, there'll be lots of other interesting things to look at if you can improve the time resolution. So I want to thank my colleagues, people who've worked in the group, and Ken's group for all the support over the years, and John and Clive for their help with the measurements. And with that, let me end, and hope everyone heard it and saw it okay this time. Thank you.